This is Vishveswaran Jothi, and my partner is Jianhang Chen. Our topic is about activity recognition on 3D based, on 3D videos, which are Kinect based video datasets using transfer learning. So we'll directly get into the presentation. This is the overview of the presentation. We are going to talk about why we chose this particular topic and what are its applications are going to be, and what are the prior works which have been worked in this particular field of study. Then what are the data sets we have used and why we have used those data sets. Then we'll explain about the network architecture that we have used and how we chose this hyperparameters, and finally the results, and then we'll conclude like what we learned from this particular project work. So the introduction is about like why we have to do video analysis. As we can see, like there are a lot of information available in the image data itself, but the image data cannot give you the concept of what is happening around you for a distributed time period or for an elongated time period. It can say only for that particular instant, or it cannot say like what is going to happen next and so on. So for that we can use a video data, and we can analyze the video data to find an activity or an event, or for mishappening like accidents and so on. So the current trends in computer vision as well as deep learning help us to analyze the videos to understand what is the concept behind each video or something like that. So we use this particular initiative, and we use that to detect 3D videos to find out whether a person is falling down, or whether the person is doing a regular daily activities, or whether there is any opportunity for the person to fall down doing or performing the daily activities. So the prior works is about like Jothi and his team. So they worked on a topic known as Beyond Short Snippets, which is presented in Computer Vision CVPR in 2015. So here in this particular paperwork, they compared the CNN and with CNN and LSTM work, where they used in one part where they used only the CNN concept, which is explained by Andrej Karpathy's work, something like that. So they compared that with the CNN in inclusion with an LSTM. So here they say that pure CNN will give us a result of about 72.6% accuracy in the test dataset, while the CNN along with an LSTM will provide you about like 84.6% accuracy, where there is no optical flow while using the datasets. So this is for the UCF hard datasets. So we use in our work the same dataset to analyze our own performances. So finally, we try to expand our work by implementing the CNN plus LSTM network into the 3D video dataset to analyze whether the person is trying to fall down or not. So this is the dataset that we use. The background gives you about like all the different classes that this particular UCF 2D dataset that consists of. It consists of indoor activities and outdoor activities. We use that to train our network. So initially we used this particular network to train, the particular dataset to train our network. Then we used that on the 3D datasets. We didn't use a particular 3D dataset, while we used a collection of 3D datasets, which is TST fall detection, and then the other two are from the Microsoft research, where one particularly gives us the indoor activities such as playing, singing, and then watching movies or playing video games or using cell phone or something like that, while the other one is about like walking, standing, falling down, another something like that. But we carefully trimmed all the collection of 3D datasets so that it has an even class distribution on the videos, and then we pruned about like 26 different class types among all the 3 datasets. So this is our entire network architecture. It consists of 3 sections. The first one is hyperparameter selection. The second section is to train the 2D networks using the hyperparameters selected on a custom CNN with LSTM, and the final one is to apply the custom built CNN with LSTM on a 3D video sets and then to test them out. So the first section is about like how we prepare the data. First we will try to collect the data, convert it into a collection of images, and then we will split the data set into training, test, and then validation dataset. Then finally we use an pre-trained inception model to extract features from it. We have a 2048 long vector feature, and then we use that to train a simple LSTM model. So we use Keras for this. In this, we use the pre-trained inception model and the Keras implementation of LSTM as the on-the-shelf or off-the-shelf available the models. And then for our contribution, we developed the CNN architecture that we are going to use it in the second part, and then we implemented that on the 3D videos datasets. So how we pick up the 3D video dataset, and then how we prune it, and then how we train it. It's our contribution on this particular work. So we run this hyperparameter selection. We run it for like several iterations and with different hyperparameters which have been randomly chosen, and then we ran it and then we found out which is the best one, and we kept the same hyperparameters. We load the 2D videos. We trained our own custom built CNN along with a simple LSTM. We tested it out. We found its accuracy, test accuracy, and once we were like confident about the particular test accuracy, we implemented 3D videos while we froze the CNN to extract the features from our second step, and then we just trained the LSTM on the 3D videos or 3D image files, and then we fine-tuned it, and then that's how we got our final results for the analysis of 3D video datasets. My friend will explain the rest of the slides.
This is the CNN architecture we use in our first section, and it contains 5 convolutional layers and 2 fully connected layers, and we put the result features into a simple LSTM. That's the CNN architecture. The following slide is how we select hyperparameters. The hyperparameters include sequence length, max frames, image dimension, and the epochs we want to chain. As you can see in the following graph, there is test accuracy versus sequence length and the max frames. The sequence length is the number of frames to present in each videos, and we tried different sequence lengths, for example 1 or 100 or 1000, but finally we decided like these 3 are some of the best sequence lengths, and the max frames is the max length of the video to be considered in each video. And finally, we choose the sequence length. The best one is 30, and the best max frame is 400, which give us the best result. And also, we also consider hyperparameter, for example, like image dimension, 100 by 100. We resize the image to fit the dataset into the memory, and if we use other dimension like 200 by 200 or something, there will be memory overflow or cause other problems. Finally, we choose 200 epochs for chaining. This slide is our result. The following the top 2 videos is from the 2D dataset in UCF 101. You can see this is the eye makeup video, and the script shows the activity, and the second video is an outdoor activity that the people are rowing in the video. And the following 2 videos is the 3D dataset from the 3 Kinect sensors, and you can see this video the people is picking up something, and so our script shows he's grasping. The final video shows one people falling down in the door. So this is our result. Our validation accuracy of the 3D videos is 52%, and the test accuracy is 46%. Finally, we learned from this project the concepts of transfer learning and the RNN, and we also think it is very important to choose some hyperparameter like sequence length, number of epochs, and the max frame size is very important for the accuracy. And we use the Kinect 3D data set for the video, just the video part, but in fact we can also use the joint data. We think if we use the joint data, it will improve our accuracy.
Thank you for listening to our presentation.
Thank you.